This afternoon, it's a very great pleasure to welcome Professor Tom Gernon from the University of Southampton, who's going to speak on the origin of the Earth's continents and oceans. Thank you.
Thank you very much for your invite to speak to you today. So my briefing was the small issue of talking about how the Earth got from a ball of hot rock, quote, into a planet that looks a little bit like this, with an ocean and tectonic plates and so on and so forth. And that transition, didn't happen overnight, of course. There's 4.5 billion years of time between these two images. And I think this is a great image just to summarize what the Earth would have looked like and all the processes that would have happened in the early Earth as we had this hot ball of rock. And of course, we have what Sarah, as great talk, has described already in terms of this magma ocean, which is a circulating body of magma on top of which we have this crust. And of course, any impacts which cascade into this crust will lead to degassing, and of course, you then have gas loss into the atmosphere and so on. So this is a really interesting state because it's quite different to the Earth that we know today, which in contrast has a very dynamic plate network, which is, of course, has been accumulated over a very long period. And you would think that because I work on the Earth and in continents, as opposed to in continents, excuse the joke, you would think, wouldn't you, that this would all be well tied up and well resolved. But actually, when we go back further in time in Earth, of course, Sarah alluded to it already, we have lots of destructive processes. We have, of course, plates moving around, crashing into each other, generating mountains, eroding mountains. And of course, we also have impacts as well. And that's not to mention plate tectonics itself. And you can see in this image here quite nicely, I can see why people are standing here now, because you can get a better view of your own slides. So you can see that today we have this much thicker crust relative to the crust on the magma ocean. And the composition of this crust is also a lot different. And we have this kind of what's called a keel, which is like the base of a ship. And this is what gives the continental crust strength and stability through Earth history. So the continents are very stable and have been for over 3 billion years. And at some point over the past 4.5 billion years, we ended up getting to a stage where this crust started to be, when it collides with the continents, it basically gets shoved down in this process known as subduction. So the ocean crust, which is more dense, sinks into the mantle, and of course that melts. And what's wonderful about that is that the oceans, of course, are the source of lots of carbonate. There's a lot of life in the oceans, and all of that stuff, spare a thought for it, because it will end up in the mantle, and it will get melted. And of course, then we get a lot of this recycling. So all of that stuff will then end up coming back to the surface through volcanoes, for example, through this type of degassing from these ocean islands, for example. So this is a very dynamic system, and the question really I want to address is, how did we go from one state on the left to the one on the right? And we did this over 4.5 billion years, as I said. We know comparatively a lot more about what happened since around 540 million years ago, which is the base of the Cambrian, when much of the sort of multicellular life had originated. And you can see that before that, everything is just shown as this pink because no one really has a clue what was going on. So there's a lot more, this pink stuff's doing a lot of the heavy lifting here in terms of splitting up these vast chunks of time into these periods, which kind of makes sense for various reasons I'll talk about a little bit later. But you can see the stuff that Sarah was talking around, the formation of the moon happened in the first, moments of the Earth formation. And so the whole sort of system, I guess, that I'm talking about today kind of evolved over the billion, I suppose, or maybe a little bit more than a billion years after this event. And of course, there's a little bit of overlap here with what we're talking about, because in the early Earth, we have this magma ocean, and I would liken it to, if you look in Hawaii into a lava lake, for example, you see these kind of polygonal cracks, and as the lava cools, So looking at the Earth would have probably looked a little bit like this. And of course, a lot of the driving forces behind all the stuff we're talking about here is heat, which is kind of intrinsic in the Earth. And almost all the talks today already talked about how this is a result of the decay of short-lived isotopes, which happen very early on and give the Earth great heat in this early stage of this magma ocean. And so, of course, I won't dwell on this too much because Sarah already has done a great job of discussing what happened here around this Earth, this Theia-Earth collision. The difference, I suppose, what I will dwell on, which is kind of relevant for the origins of the continents, is that, and this is relevant to a question as well as someone asked, is that it's been recently suggested, I'm not saying I agree necessarily with this proposal, but it's been suggested that maybe some of these weird anomalies that you get in the base of the mantle, they're sometimes known as LLSVPs, these large low-velocity provinces, may actually be a fragment of the impactor of this planet, Theia, which ended up being incorporated into the Earth. And those authors have produced a simulation of that process, and you can see how the material here is, from the impactor, is kind of then homogenized. And that is what shapes, I guess, the composition of the Earth's mantle, and therefore also the crust, which is what I mainly want to talk about. This is quite tantalizing because these isotopically anomalous provinces in the deep mantle, they have a big impact on the composition of stuff erupting in a lot of volcanoes at the Earth's surface even today. So this was a controversial idea, and I don't think everyone agrees with it, but it's just showing you that's quite a useful thing to know about geology. There's a lot of debates about these kind of things still because they are intrinsically uncertain, and we're working with various constraints which have, been around a very long time. So this is very much open to debate. Sarah also talked about the constant flux of material to the Earth's surface, which brings all these weird and wonderful chemical species that she's discussed, and that includes water. And it's thought that the final, I guess, segregation of the Earth's core will have mopped up a lot of the water that was available. However, it's quite interesting to note that if we look at the composition of the mantle based on rocks that erupted, for example, the Earth's mantle contains more of these siderophile elements, as they're called, which basically like to go into the core. So these include gold, iridium, and platinum group elements. So we have more of those in the mantle than expected if they were all sucked into the core when it initially formed. So that's led to suggestions that there was this late veneer event, which may have happened between 4 and maybe 3.5 billion years or so, probably even earlier. And this late veneer basically dusts the planet with all of these kind of ingredients, including water and maybe some of these amino acids and so on. So that's quite an interesting proposal, and there have been rocks studied on Earth which are quite old, around 3.8 billion years, and they have been kind of attributed to some of the heterogeneity that may arise from this kind of messy system if we have lots of material introducing here. I must say some people also support the idea that actually a lot of this stuff didn't come in one veneer event, if you like. It was actually more continuous through Earth history, and I think that's probably hard to separate in some ways from this idea. So this is, based on that, we end up with this system where we have the core segregation quite early in Earth history. I just thought it was worth noting that there have been a few papers come out recently that have actually said that the inner core formation occurred potentially much later in Earth history, so as young as maybe 600 million years ago. So this is a sort of an ongoing suggestion that this early, or late, I should say, inner core segregation may have been a kind of quite a rapid event that coincided quite interestingly with the evolution of first multicellular organisms. Some people have linked those events. It's quite useful sometimes to take a step back and think about, well, how much water is there in the Earth's crust? So this is typically the amount of water including the oceans and within the crust, is less than 5%. So it's a relatively small component, really, of the Earth's crust system. So, and this is quite a good diagram because it also shows you what the color of the mantle is. We often think of the mantle as red or orange, which is in textbooks. It's actually green because this is basically comprised mainly of olivine, which is a green mineral, a very hard mineral, which has comprised most of the mantle. So we know that the Earth's surface was largely water-free just because it was very hot in early Earth history. And over time, I guess, it will have transitioned to a cooler climate in which we had liquid water. However, we don't really know the time scale of this transition, which is quite frustrating. But I do want to show you some examples of features which have allowed us to constrain what that might be. Previous talks have already talked about the origin of much of Earth's water, which of course makes up the ocean. So I'm not going to dwell on this too much. Much of this primordial water, I guess, which has ended up in the mantle, from some of these, for example, collisions from this veneer and these processes, will have been degassed from volcanoes, which again were very active in this early Earth period because much of the heat needed to escape to cool down the planet. So lots of water had ended up outgassing to the atmosphere through volcanoes. We know today that volcanoes can vent about 70% of the gas, I guess, that comes out as water. I must stress that's today, so that's quite different because we have an active plate tectonic system. Of course, we had condensation of this, but the Earth's surface remained very hot in the first probably 500 million years of Earth history. And it's likely that the ocean kind of first formed en masse around 4 billion years ago, although again, this is debated. I should also say something brief, although it's not the remit of my talk. It's worth noting that the early oceans were very oxygen poor, as was the atmosphere. So the Earth's atmosphere was initially very reducing, so we had lots of hydrogen, carbon monoxide, dioxide, and nitrogen. But it was overall much more reducing than it is today because there was still iron present as the core sort of formed early on in Earth history. And the oxygenation, mysteriously, I guess, only happened after about 2.3 billion years ago, which is roughly half the way into Earth evolution. So that's kind of an intriguing period in Earth history, which has also coincided with one of these major glaciations that Sarah talked about. And tantalizingly, we had a second phase of oxygenation around 700 million years ago, which also coincides with a major glacial period, the snowball Earth period, when people think the entire Earth was covered in a carapace of ice. So, yes, the early oceans weren't very nice places to be if you were there, because they just were pretty toxic. How do we know then about the earliest fragments of Earth's crust? And there's a great mineral known as zircon, and zircon is a little bit like people would say a time capsule. I think of it as like a flight recorder, because these crystals are very hard and very stable through Earth history. And so these crystals, which are a type of silicate, neosilicate, they form and they kind of capture sort of the chemistry of the material they're forming from, I guess, within these zones. So they're a little bit like trees, when you cut a tree and you see the growth rings. So these crystals contain these growth rings, which we can analyze, and then we can therefore understand, the conditions that they represent. And so the isotopic evidence, the chemical evidence from these zircons tell us that water was actually present in the melting source as early as 4.4 billion years old ago. So that was when some of these first zircons formed some of the first material on the oldest material on Earth that isn't meteorite, is from this Jack Hills locality in Australia. And more recently, there's been a paper that's used various kind of machine learning approaches to look at a multitude of these crystals. And they found evidence that there's a sort of possibly a sedimentary source for some of these zircons. And what that's telling you is quite tantalizing. It's telling you that maybe even by 4 billion years, we had material going down into the mantle in sedimentary, like rocks, and then coming back up and melting again. That's quite controversial. Some people would say, hold on, maybe this is just an impact. If you have an impact, you can quickly get stuff from near the surface, potentially into the mantle through other means, and there are other ways to get stuff into the mantle. So just so you know, this is quite a heavily debated field. And if you want to know how much geologists actually argue, you can see in this diagram, this is sort of when people think the continental crust formed. And you can see that there's a wild range of constraints here. It's probably just as well my laser stopped working, so I'm not able to point out specific examples. But I think you get the message here. There's a lot of debate about this. And there's a reason why there's a lot of debate about this. And I think you can see the Goodwin curve here on the right, the brown curve. I think that curve is a measure of the amount of crust preserved of a given age. And so the amount of material is sort of exponentially less as we go further back in time. So we deal with some remote, localized outcrops. And there may be a few rocks, and sometimes they're very hard to get to, and they're very hard to access for other political reasons. So there's a lot of reasons why there's so much debate about crustal growth and when things grew. So I think that's quite interesting. Well, what's not debated is that the early Earth was very hot, and we had lots of weird types of volcanoes erupting, which were much hotter than today. And that includes things called komatiites, which are like basalts, but they're much hotter. So, and that will have an effect on the crust itself. Do we know how plate tectonics evolved? Not really, but there's been various suggestions. And so I'm going to take you through a couple of those suggestions, and I'm not going to dwell too much on that, but just in terms of my personal preference on these. But there's this nice one called squishy tectonics, whereby we have this situation here where we have these kind of what would be described as proto-rifts, so very early stage rifts of the Earth where the crust is possibly moving apart. And that will promote upwelling, and that upwelling, as you can see in these purple regions, will drive melting. And that melting in turn can start to melt the parts of the crust which had segregated or cooled over time. And that forms something which has a different composition, which is more felsic. It's got a lot more silica in, which is more similar to what we have on the crust today. So you can see that we may have had this Earth's crust emerging, quite slowly from this kind of squishy system. There's a hint in this diagram that there may even have been some of the red stuff, which is the basalt crust, maybe going down because it's dense. So kind of a very early stage plate tectonics almost emerging from this picture. And one thing which has been proposed as well is the concept of heat pipes. Heat pipes are, as they suggest, they're basically these kind of planes, I guess, through the early forming crust which allow heat to escape to the atmosphere. And by virtue of having these heat pipes, we can basically cool and thicken the crust, so we get a much thicker crust early on in Earth history. And as those eruptions then start to decay through time, presumably due to the cooling of the planet, we have thinning of the crust again before it thickens, related to conductive cooling, related to the stagnant lid regime, as it's called. So this is related to like steady thickening and strengthening of the Earth's kind of early primordial crust. And that's shown here, like in contrast to a more mobile plate tectonic network shown on top. On the bottom, we have stagnant lid convection, where we have convection in the mantle, but nothing's happening in terms of the top plate. It's not really being brought down necessarily. And something that we know that is required to have plate tectonics, to have plates actually being shoved into the mantle, is some mechanism of weakening them. And a great way of weakening rocks is to wet them. And we know this from even from engineering geology. You know, if you're studying, it's quite important to study how bridges can collapse and so on. We often use experiments to constrain the strength of material. And of course, we know that water-saturated rocks are much weaker. And so the idea might be that plate tectonics actually really only got going as soon as we had a lot of water around, which could basically cool and weaken the lithosphere. But before that could happen, there's a suggestion. I think this is a really cool idea because it's not just based on models. They have some nice geodynamic models here of what this early kind of plate tectonics may have looked like. But they also have looked at rocks as well, and they found evidence that you get these short transitions between what are volcanic arcs, and volcanic arcs form at the collision between plates when a plate's been subducted. Places like the Caribbean, for example, today is a volcanic arc. So they find rocks which have chemical similarities to arcs, and then they have non-arcs not long after, and there's almost this episodicity in early Earth history. And this Moyen and Van Hoonen paper, when they studied what would happen if the plates were a bit warmer than they are today, what they found was that the plates were much weaker and they basically broke much sooner. So we couldn't subduct the plate all the way down into the mantle. Instead, it breaks off. And so that might kind of give you a very sluggish onset to plate tectonics because you're kind of getting going and then it stops and it may take a while to get going again. So there's this kind of idea I think is quite good and a kind of based on observations as well and models that there's this very sluggish stop-start plate tectonics in the Archean, that is in the first, like up to about 2.5 billion years ago, possibly much earlier than that. Of course, we got to mention asteroids because these things are continually smashing into the system as it's trying to establish plate tectonics. And of course, asteroids, as we've already heard today, can lead to enhanced melting in the mantle through various mechanisms. And one of those is exemplified by the other debated issue, which is Chicxulub, where you have the antipodal sort of potential melting on the other side of the planet related to the asteroid impacts. But there's been some studies looking at impact-initiated subduction scenario. And these guys basically studied what would happen if you have an impact in terms of mantle, like circulation and so on. And what they found was that even by having fairly moderate impacts, you can influence, without actually maybe necessarily generating melting from that impact, you can modify the surface of the planet in such a way that you can thin what lithosphere there is, whatever crust there is present. And that thinning then weakens the lithosphere and it can cause upwelling, which can cause melting then. So it's a sort of a secondary, I think, effect of the impact that we can influence the melting, the thinning of the lithosphere, and also the circulation and possibly upwelling from deeper levels through various feedback mechanisms linked to that rock, space rock colliding with the Earth. And then there's been other suggestions quite recently. This is a paper by Johnson and people like Mike Brown, and they kind of speculate. This is, by the way, from the ancient Pilbara Craton, which is a very stable bit of the Earth's crust in Australia. And they're talking around 3.5 billion years ago here, and they've suggested that you have a large impact which causes evacuation. And of course, as a result of that, you have rebound, like isostatic rebound in the middle, of where the impact crater was, which allows then infiltration of seawater into the fractures generated from this impact. And that can basically give you this hydrothermal alteration of the crust, which weakens the upper crust as well. And as a consequence of the impact, you then have upwelling and melting, and this then gives you kind of a weird, quite dense nucleus to the continent, this mafic, ultramafic plateau, as it's called. And some of this stuff is so dense that it actually then drips into the mantle. And I think that's quite an interesting mechanism because it can lead to refertilization of the mantle. It can basically lead to bits of crust, early form crust going down into the mantle and refertilizing it, so potentially explaining some of the isotopically anomalous bits of the mantle. And I think you can imagine from thinking about a lava lamp how this dripping may actually operate. We have an unstable kind of boundary layer between two fluids, one being more dense, and as it sinks, then it in turn promotes upwelling of whatever is to fill the space of what was left behind. Very good, thank you. So this dripping then sort of, I guess, modifies the lithosphere in such a way that may thin it and may weaken it. And there must be a critical point then at which we can actually start to subduct the crust, which at this stage is quite mafic, this oceanic crust. So why can't we just be more categoric about all this? And I think the reason is that the ocean crust is quite a recent phenomenon in terms of the preservational bias on the Earth. So because we have subduction, most of the crust dives into the mantle and gets melted and recycled. So the oldest oceanic crust, categoric oceanic crust today, is around 250 million years old. So when we get back to 3.5 billion years old, we rely on other bits of material which look like ocean crust, which instead of going down, almost accidentally get shoved up onto continents. And this is a process known as abduction, and this is what led Cyprus to being where it is today. There's a piece of oceanic crust that gets shoved up instead of down. And fortunately for us, there's a fragment of this type of crust preserved in Greenland called the Isua series. And what's interesting, if you took any of these lines of evidence in isolation, you may not be able to say this is categorically oceanic crust, but the combination of features that we get in this outcrop, including pillow lavas, which are kind of synonymous with lavas erupting into seawater, you get cooling down and you get these kind of pillow lobes, which kind of squeeze out and like toothpaste and jump on top of each other, and you get these kind of very characteristic forms. And the other really cool bit of evidence is that you have lots of carbon or graphite-rich sediments within this sequence. And so some authors have looked at the carbon isotope composition of this, and they've also looked at the morphology, I guess, of the graphite or graphene within these sequences. And they argue that they are actually early forms of life. They are organic material, biotic formed carbon based on the sort of tubular and hexagonal kind of forms that are present within these schists. So this may be the oldest evidence for, a very active ocean system around 3.8 billion years ago. Just lastly then, to sort of think about the preservation of the Earth's crust today, all of these kind of purple and pink areas are known as the stable Cratons. These are ancient cores which are almost like armored. They're like tanks, of the crust. They're really strong, and they are present on nearly all of the continents. And these are typically between 150 and 300 kilometer thick regions of the crust formed by the processes that we discussed already. And what I think is quite interesting is that these time capsule minerals known as zircons, we've analyzed thousands, possibly tens of thousands of these zircons through Earth history. And as I said, they're almost indestructible. But what we see is these peaks in the appearance of these zircons through time, which appear to correspond to what's known as supercontinents, periods when we had all the continents kind of glued together in this mass, which represent periods of crustal growth. And it's important to say this is a preservational bias as well in zircon, because it predominantly kind of picks up the growth of supercontinents. It's not necessarily always representative of other stuff that's going on the planets in between. And lastly, something which I think is really quite fascinating is that when we look at diamonds, which almost exclusively occur in those regions I just showed you, these diamonds, they don't just form at one point in time. If we take any particular diamond mine present, these are examples from Africa, we see that any given diamond mine may have 4 or 5 or even 6 populations of diamond growth. And these diamonds are forming under high pressures and relatively low temperatures at the roots of these ancient continents. And it's likely that these diamonds are forming from carbon which has accumulated through like subduction, through this kind of conveyor belt, if you like, of carbon, which brings the stuff from the ocean bed into the mantle. And just in terms of thinking about origins, it's really interesting that some of the oldest diamonds, I'm afraid De Beers were lying when they said diamonds are forever, because they're actually, the maximum age we can see are about 3 billion years old. But this corresponds quite tantalizingly with the period when we think plate tectonics was becoming established. And so it may be that diamonds that you're wearing could reflect that process. And it's also interesting to note here that the diamond growth also appears to correlate with periods of big continental collisions, big like car crash between continents, if you like. And I just want to finally, this is something I shouldn't have left 2 minutes to talk about, the origin of plate tectonics. But it's quite interesting. There's a lot of kind of interdisciplinary observations that go into plate tectonics. That's how it was devised as a theory, I guess, bringing together all these observations. And I think what's worth pointing out here is that there was a sort of a change in just volcanic rock chemistry that seems to happen around 2.5 billion years ago, shown by this gray field in the left-hand diagram. And this is picked up through various chemical indexes, such as, for example, rare earth element ratios, or various major elements like magnesium, for example. But we see that there's evidence that there's maybe a decrease in the amount of melt in the mantle, and that could reflect cooling down of the system. And I think the other really cool bit of evidence is that when we have subduction, which is the best kind of evidence of plate tectonics, I suppose, you get these two regions. You get a region where you have very high pressures because the continents colliding, but it's also low temperature because we have seawater being dragged down, cooling it down. So we have high pressure, low temperature rocks. And we also have really nearby high pressure, high temperature rocks. So the difference being high pressures, but the temperatures are high, related to the magmatism caused by the melting as this water is introduced into the wedge below. And what's really cool is when we look at metamorphic rocks, we can actually see this kind of what's known as paired metamorphism, this juxtaposition of these two regimes in Earth, in conditions. And we can see almost in metamorphic rocks that they kind of appear to originate around prior to 2.2 billion years ago. So taking all this information together, it seems very likely that plate tectonics emerged, I guess, around 3 to 2.5 billion years ago. And I don't think plate tectonics happened overnight. I think it was a kind of diachronous and a quite steady kind of transition from one regime into another. I think globally it may have been a very heterogeneous onset of plate tectonics. It didn't happen everywhere at the same time for some reason. And that's why geologists complain and argue with each other. So there's a lot of uncertainty involved, and that's why geology is interesting. So just to conclude, water was present. We know that from zircons, which formed around 4.4 billion years ago. But the first evidence of quite convincing ocean crust is younger. It's around 3.8, maybe a little bit close to 4 billion years in some examples. About 70% of the continental crust was formed by the end of Archean, and that's kind of consensus if you looked at those graphs. And we had this kind of transition in Earth history from the magma ocean through to a functional plate tectonic system where it went through various regimes, which may have included squishy tectonics, heat pipe tectonics, and stagnant lid tectonics, where the plate is basically one major plate on the surface of the planet. And just to finalize, the evidence then of modern-style plate tectonics seems to be categoric around 3 to 2.5 billion years ago. And maybe this is related to some threshold being crossed in the Earth system, possibly related to the availability of water and the weakening of tectonic plates. Okay, I will leave it there. Thank you very much for your attention.
Thank you very much. You're happy to take questions?
Yeah, absolutely, yeah.
I think we've got 10 minutes to record our questions. And a couple of hands went up very quickly over there in the middle.
We seem to be in a situation where, roughly speaking, half the Earth is ocean and half is land. So is that just a coincidence, or is there any feedback effect that would tend to segregate the water and the land?
Yeah, I think the divide is around 70% ocean, 30% land or something like that. But yeah, I think thinking about, I guess, and to some extent the zircons helping here, we know that the crust, I guess, that forms the continents was formed over time. So presumably, we had episodic growth of the continent. So the land area effectively will have changed through Earth history. And so it won't have always been 70-30. Your question is more if there's a fundamental control on that in terms of plate tectonics. And it's possible there is, because when you think about it, the continents, and this is how the zircons are useful in the first place, the continents are continually being denuded by rivers. We have hydrological cycling, and all that stuff ends up being brought into ocean basins. And we've already learned that those ocean basins don't survive because they're subducted. So all that continental material brought by glaciers, by river systems, ends up being brought down into the subduction channel and remelted. And that will then kind of erupt as volcanoes, like arc volcanoes. So it's likely that a lot of the material is recycled. So there may be a kind of a fairly steady state being reached, because the subduction zones, we think of the Pacific Ring of Fire, for example, we have all these volcanoes which are degassing, but they're also bringing a lot of more silica-rich material related to the melting of that sediment that's being dragged down against its will into the mantle. So I'd like to think that it reaches a kind of steady state. Who knows whether that will be the case, through the future. So,
okay.
Thank you.
I think this side's been rather unrepresented. The gentleman at the front.
Yeah.
You showed a plot of the wild disagreements in the growth of the crust over time. Could you elaborate on how so many different models have been so different?
Yeah, that's a really good question. I think it kind of depends. Personally, I think it's related to the fact that when we get back, I was at a conference recently where some people showed some geochemical data whereby between two data points we had something like 600 million years. So it's slightly wildly speculative what happened in that lost time, So a lot of the kind of estimates then of what the crust could have been are related to kind of assumptions or related to models, geodynamic models, which themselves will include assumptions. So I think it's that. I think it's the fact that people don't necessarily use the same assumptions in the geodynamic models, but also related to the fact that we have less rocks, and so we have fewer constraints back in time. Yeah.
What sort of assumptions are they making?
Just in terms of the crustal growth, yeah, related to the temperature, and I suppose also related to the amount of material that's being formed. And that's ultimately, that's kind of variable depending on even which tectonic regime, I guess, you're considering, yeah.
Oh, thanks.
Thank you.
And there's another one on that side. And I'll come back to it.
Hi, thank you for the lecture. I was just wondering, in terms of the asteroid that wiped out the dinosaurs, did it change the structure of the tectonic plates in any shape or any form?
Yeah, so maybe there are people who are more qualified to answer that question than me. Just in terms of the Chicxulub impact, I think there's been a lot of work done on that recently because they've been able to drill into the crater itself. And without doubt, that's a huge impact, and it caused a massive sort of transformation in the crust locally. So we see lots of very heavily brecciated, basically broken up rocks around the crater itself. Whether that then transferred, kinetic energy from the impact, had an impact on melting, on the antipodal, I guess, to that is another question. So the Deccan traps, for example, the outpourings of basalt in India, which appeared to correlate in time to that impact. It's becoming clear that the timing kind of link isn't as categoric as people used to suggest. And it's probably more likely that actually the volcanism that was happening on the other side of the planet had started a little bit earlier than the impact itself. So while it's kind of interesting to speculate on the links to that impact, I think generally there's a feeling that the impact itself, some climate feedback through the impact itself were more important than the volcanism. But that is a hugely contentious issue, and there's different camps sort of arguing either way with that. Yeah.
There was another question over here. And then there was someone in the centre.
Hello, thank you. 2 days ago, I was actually going around the last of the bell foundries we have in this country, where they cast bells out of bronze. But when they do this, they melt down their bronze in a furnace, and when they've got it, the last thing that happens is slag comes to the surface, and this is all the impurities they don't want, and they scrape it off, throw it away before they do their casting. But it struck me that that sounds analogous to our continental crust.
Yeah.
Is that, in fact, when the Earth was molten, something like bronze, I know it isn't, but and the continental crust in any way analogous to the slag that floats on top of?
I think in a general sense, yes, because it's basically all the impurities, the sort of light stuff segregating and floating, and you get a much more silica, so less dense crust forming as a result of that segregation, basically, yeah. So,
which is
and of course, the heavy stuff sinks and forms the core quite early on. So it is an interesting analogy, and of course, when you see a piece of slag, you also see that it's quite vesicular. It's got a lot of bubbles in, so there's volatiles that are escaping, in that process. And that's quite useful as well, analogy, thinking about the crust, because as it cools, the volatiles will have escaped and enable the planet to cool down as related to that as well.
Thank you.
Yeah.
There was a question in the centre. 2 questions in the centre, it seems.
Thank you. Is the stagnant lid tectonics that which is thought to apply to Venus which is why Venus doesn't have active tectonics, but just has volcanoes popping up.
Yeah, again, that's something that there are other people here more qualified to talk about. Having said that, I have a colleague in the States who's tried to interest me in this problem, because Venus is one of the planets which is believed to possibly have Cratons, is that right? So it's possibly got some kind of ancient Cratons, which are kind of visible, I guess, but not in high enough resolution to really speculate any further. I think there's some upcoming missions in the next decade which will be looking into that. So it's kind of hard to say. Like the presence of Cratons, if they are Cratons, is interesting because it probably tells you that you're somewhere in this regime.
Is it all Craton and no subduction?
Yeah, I don't know. You can only speculate. That's why we need missions to go there, which is, I think I've heard this a few times today. Basically, if you just observe the Earth from a distance, it would be very hard to kind of, speculate on things like that without the chemistry. The chemistry is what really is deterministic in pointing to plate tectonics and the carbon cycle, the circulation of material. Maybe we'll be able to resolve this in the next few years.
And your neighbour had a question.
Okay.
Yeah, my thoughts are conservation of energy. Correct me if I'm wrong, the source of energy that causes the plate tectonics, which is a large amount of energy, methinks, comes from the core of the Earth primarily. Is that true? Yeah, not from solar gain or anything like that.
That's right. Yeah.
Won't there be, that's not an eternal supply of energy. Therefore, should there not be a diminution of plate tectonics over time? And will eventually, assuming we're not subsumed by the sun before that time, will the Earth be an earthquake-free zone? I mean, so it should diminish over time.
Yeah, and you're right, it is. I mean, the Earth is cooling.
Yeah.
And what's kind of interesting for me is, and this is kind of related to one of the last slides I showed you, we have diamond formation. And diamonds are quite a useful bit of information because they're very picky about the conditions they form in. They have to be high pressure. They have to be fairly low temperature. They can't form the oceanic environment. It's too hot. But through Earth history, if you look at the distribution of diamond-bearing rocks, there is a huge peak that has happened in the last few 100 million years. It's called the Cretaceous kimberlite bloom. It's about 200 or 300 million years ago. And why I think that's interesting is even if you account for crustal preservation bias, if you account for that, you can't remove this peak. It's not just related to preservation. And so I think it's because the Earth is cooling down. And so you get this Goldilocks zone at the root of the continents where the conditions are just right for diamonds. And I think that the fact that we have most of these forming from the Cretaceous or maybe Jurassic onwards is evidence for that, the cooling of the Earth, and that your crustal thickness changes to a point where the roots of the cold, high-pressure roots of the continents are just in the right zone for diamonds to be stable as opposed to graphite. So, I think over time then, the implications of that are interesting because, of course, plate tectonics will eventually die, and then we'll have, as you say, less in the way of all the expression of plate tectonics, including volcanism, earthquakes, where plates are colliding. So, yeah, that's
don't want to do you out of a job.
Yeah, for sure. That's the thing.
And there was a question over there. And
thank you. I'd like to ask you a question about the early history of water on the Earth. You mentioned that there's evidence for the presence of water through zircon crystals at 4.4 Ga.
Yeah.
But the oceans, you mentioned, only formed at 4 Ga. Do we infer from that during that 500 million years, initially there wasn't enough water to form the oceans, and that this was provided by asteroids?
Yeah. When I say 4G, I think there is a grey area there. So, as I've discovered today, it's also called a purple area when you're thinking about the universe. I would say the zircons that formed at 4.4 GA, and some of those zircons from that locality range in age to about 3.8 GA. But they suggest that the magmas from which they crystallized formed had water in, which is different to suggesting that there's a surface ocean, I guess. So presumably the Earth's surface was too hot for that first few hundred million years for liquid water to exist at the surface. But I suspect as we move towards maybe 4 billion years, that you would have maybe the condensation that happens in the atmosphere enables eventually hot, warm pools that Darwin called them to form at the surface. And I guess then, as I said, around 3.8 billion years, we have evidence for seafloor proper, which has evidence that the volcanic material being erupted on the seafloor was into the ocean. So I think there's a kind of probably a protracted kind of boundary between all these things. And early on, you don't have like an ocean per se, but your water is within the mantle. And it's entering the atmosphere through degassing from volcanoes more and through collisions, I suppose.
Thank you.
I wish I could give you a more categoric answer than that, but that's the state of play, really. And ideally, I think when we think about this, and I think this is, if you read some of the commentaries and some of the recent papers on the zircons, people keep saying, oh, we need more localities, we need to be able to find more of these things. But the realities are very hard to find because they're just so rare, So we don't have a very good record of a rock record for that period, prior to, in like during the Hadean and in very early Archean. So that's why some of these, like Jack Hill's zircons, have been doing a lot of heavy lifting, and this is why this field is quite contentious. There's just a lot of unknowns as well. So.
Thank you.
Any further questions? This one right here.
I'll apologise now because it's a bit more blue skies, but right at the beginning you mentioned about the Thayer collision and it may or may not exist in, I think you called it like a low viscosity anomaly.
Right. Yeah.
Is there any way to determine that, like if you use carbon dating or tungsten hafnium dating in order to like isolate a planetary genome within another planetary genome?
Yeah, I'd like to think that was possible somehow. I mean, what's kind of quite convenient about these low shear wave velocity provinces is that they are thought to be linked to volcanism at the surface. So like even today, like the East African Rift, for example, has this large low shear wave velocity province, and the other place is the Pacific. So there are two of these either side of the planet, and I think they were showed in some of the diagrams from that bit. But yeah, presumably you're going to see evidence for that in terms of like primordial, like tungsten isotopes and various things. I would say what's quite interesting is like geology is a little bit like a crime scene, and you're going around like a forensic scientist trying to pick like pieces of evidence to determine what the cause is. And when you look into the detail, even today, those large velocity provinces, they're in regions where they've been proposed to like support the crust. They are dense, like these regions are dense, which is why they've been linked to maybe possibly forming from this Theia collision. They could be a part of the impact that gets incorporated into the Earth. And so they have a really interesting expression at the surface today where we have like topography. And so people have linked the topography to these, what I would describe as thermochemical kind of plume-like features that come from the deep mantle. But the problem is a lot of the stuff that erupts around that time chemically is quite distinct. It's not really necessarily showing a really deep signal, like a very hot, deep plume. And it's another whole story I could get into, but we have some ideas on what it is. So when continents break up eventually, it kind of sends this kind of wave beneath the continent, which could have another effect on, it's called like mantle wave. We published this in the last year or two. So there's other reasons why, you know, things that have previously been kind of attributed to these deep thermochemical anomalies, when we look into the details, sometimes we don't see the kind of primordial signals. Some people have looked at kimberlites. Kimberlites are like these diamond-rich magmas, which were previously thought to be really deep. Again, the more you look, the more you find they're probably quite shallow, like 200 kilometers or maybe a little bit more. But people have used tungsten isotopes to fingerprint them, and there is very limited evidence for like these deep plume sources for kimberlites. Yeah.
I think that's brought us up to our time for tea and coffee break. So can we just thank both our speakers for this afternoon?